Hello viewers, today we are going to see about dynamics of harmonic oscillations. The oscillations of a physical system results from two basic properties, namely elasticity and inertia. So to prove this statement, we once again go back with our earlier system connecting a spring that has been stretched, and based on that we have a restoring force. So we can relate this force with displacement. So the restoring force is directly proportional. Restoring force is directly proportional to the displacement. Displacement is here it is y, and directed towards the mean position. So a spring that has been tied attached firmly to a solid base, when it is stretched, it tries to oscillate about its mean position. And the restoring force, we apply one force and there will be a restoring force. It is directly proportional to the displacement, and it is always directed towards the mean position. So force is directly proportional to the displacement. So the constant of proportionality is K, which is called force constant. Force, the restoring force and the displacement is related by with a minus sign, just because both are in opposite directions. And also we have force is equal to mass into acceleration. Force is equal to mass into acceleration. This is by Newton's second law. So this is by Newton's second law. So now we have two equations. Making use of these two equations, we will derive, we will equate and we will derive for acceleration or displacement, whatever we want. Okay. So we have two equations. One is force, which is equal to minus ky, and another equation is force is equal to mass into acceleration. This is by Newton's second law. So we can equate this equation with this equation. So mass into acceleration is equal to force, this side minus ky. Therefore acceleration is equal to minus ky by m. Okay. So from simple harmonic motion, in simple harmonic motion, acceleration is given by minus omega square y. This we have seen in the earlier video while deriving for acceleration, velocity and displacement. So what we can do is, we can substitute, we can equate these two equations because both are accelerations. So in simple harmonic motion, acceleration is given by minus omega square y, and this acceleration we equate these two equations and we get this one. So now we can equate these two equations. So minus omega square y is equal to minus ky by m. Now what happens is, this y gets cancelled, minus gets cancelled. So we have this omega square, this y and y gets cancelled. Omega square is equal to k by m. Minus gets cancelled. So omega is equal to square root of k by m. Now we all know that omega is equal to 2 pi f, where f is the frequency. In textbooks they relate by n like that, but We can represent by this way also. 2 pi f omega is equal to 2 pi f, which is equal to square root of k by m. Now here f is equal to 1 by t. F is related with the total time period by 1 by t. So in the place of f we can substitute 1 by t. So 2 pi by t is equal to square root of k by m. You bring this t this side, move these terms to the other side. So 2 pi square root of m by k is equal to t. That is, the time period is given by the time period of simple harmonic motion. So time period of the simple harmonic motion of the particle is given by t is equal to 2 pi square root of m by t. Okay. That is, it depends on mass of the particle and the spring constant or force constant of the particle. Therefore, this can be said in simpler terms as t is equal to 2 pi times square root of inertial factor divided by spring factor. Just to remember, we can say in a broader notation that time period depends on 2 pi multiplied by square root of inertial factor. Inertial factor is due to the mass of the particular particle. So it has inertia. If you want to try to move a particle, you need it opposes. So therefore it has the inertia. You have to overcome that inertia to move the particle. Also we have K, the force constant or spring constant or spring factor. That's why we said the dynamics of harmonic oscillations depends on elasticity. Elasticity is the term related with spring, because spring, when you move it has to regain its original shape. Therefore it has elasticity, and inertia is due to the mass of the particular particle. Therefore the time period or frequency depends on inertial factor and spring factor. So the final conclusion is the time period depends on 2 pi into square root of inertial factor by spring factor. So this is the basic understanding of the dynamics of harmonic oscillations. It depends on inertial factor and spring factor. Hope you have understood this topic. Thanks for watching. Nandri.